All right, so today we're going to start with advanced cryptography and PKI. Click on the right screen. All right, so we're looking at how to implement cryptography. Look at digital certificates, the public key infrastructure, different transport encryption protocols. All right, so if you have cryptography and you don't apply it properly, you can have vulnerabilities in this. Some things you need to understand when you implement cryptography include the key strengths, secret algorithms, block cipher modes of operation, cryptographic service providers, and the use of algorithm input values. All right, the cryptographic key, that's the value that serves the input to the algorithm. And then what does it transfer the plain text into ciphertext, or does it the opposite way for decryption? Now we got three primary characteristics that's going to determine the strength of the key. Okay, we've got the randomness, the length of the key, and then the crypto period. That's the length of time for which the key is authorized for use. So by using these together, we can build a strong key for our cryptology. All right, so looking at this, we see here that we got a key length of 3, and a key space 17,576, and the average number of attempts that's needed to break it's 8,788. While we look at that and think that may be really secure, because you're thinking somebody's going to sit there and try to break it basically almost 9,000 times before they get it, you're going to think that a lot of these are coming through. These attacks are not going to be somebody typing this in. And these attacks are going to be generated by a computer. It won't take a computer long to break that encryption. Whereas if we go down to the key length of 8, we see that the average number of attempts needed to break this would be 104,400,000,000 million. Okay, so the longer our key, the more secure it will be. The strength of it will be better. All right. So we talked a little bit last week about the strength of cryptography is not in the algorithm. The strength of it is in the key. And so this is an example of why. This is why the algorithm is not as strong as the key, because for it to be used, that algorithm has to be known. Okay, it has to be widespread. They give an example here: military force uses cryptography must allow many users to know the existence to use it. If I write down a message like we looked at last week, if I just write down random gibberish and hand it to you, and you have no idea what algorithm I'm using, there's no way for you to decrypt it. So by knowing the algorithm, and if you know the key, you can decrypt it. All right, block cipher manipulates entire blocks of plain text at one time. Plain text is divided into separate blocks of specific lengths, and then each block is encrypted independently. So we see some common modes here. We got the electronic code book, cipher block chaining, counter, the Galileo's counter. Crypto service providers allow an application to implement an encryption algorithm for execution. What this typically does is it does implement cryptographic algorithms. It will generate the key, provide key storage, and authenticate users by calling various crypto modules to perform specific tasks. And this is something that can be provided in either hardware, software, or both of them. We see an example here on the screen for the Windows 10 cryptographic services. All right, some of these algorithms are going to require that in addition to the key, another value can be used or inserted or inputted for this. For example, assault, that's a value that can be used to ensure the plain text, when it's hashed, will not consistently result in the same digest. The nonce is an input value that must be unique within some specified scope. And the IV is the most widely used algorithm input. All right, digital certificates. These are something that's common. When you use this, you need to understand their purpose, know how they're managed, and then what digital certificate is going to be appropriate for situations. Digital signatures, that's used to prove that the document originated from the sender. Okay, so this is something that they're going to digitally sign saying that I sent this. So it will show the private key of the sender was used to encrypt the digital signature. Now, with this, the weakness is the imposter could post a public key under the sender's name. So the example here, all right, so we see Bob's public key is 2111984. So he's sending out this encrypted message and it's going to be signed. So he creates the message and the real message says buy stock now. Now in this, Mallory is intercepting this message and it will create an imposter key. And you see the two keys don't match up and she's sending the message that says sell the stock now. Well, once Alice receives the imposter's public key, then they're going to sell the stock. All right, trusted third party. This is used to help solve that, the problem of verified identities, because it verifies that the owner and the public key belong to that owner. And it helps prevent that man-in-the-middle attack. It helps prevent that person intercepting the messages and generating another key. Digital certificates, technology used to associate a user's identity to the public key. Okay, so that's where you've got it digitally signed by a trusted third party. So if I was going to send you an email and I was going to have it signed by a trusted third party, okay, we could say that we would trust, say, the IT department of GTC. All right, let's say that they issued these certificates. I would have them sign it saying that it came from me, and then when you got it, you could verify that, okay, we trust this third party to tell us the truth about where this came from. So you do have some people like the certificate authorities or tools for managing certificates. These are things that are used to manage the digital certificates. The CAs are responsible for digital certificates. You may some called root CAs. Now with this, if you want to use a digital certificate or you want to you generate your private keys, you complete a request for information. It's got your name, phone numbers, email address, different information they're asking. So way they can verify your identity. And it's known as a certificate signing request. So then the user is going to sign that electronically, send it to a CA, and it's going to be processed to verify the authenticity of the user. All right, so in this car title scenario they're giving you, and then the digital certificate element equivalent. So the car title application would be the same as a CSR. You're filling out the information. When you sign the car title over here in the digital certificate, you're creating and affixing a public key to the certificate. So it's like adding your signature. Visit the county courthouse. So this, you send it to the CA. And finally, the title is sent to the state DMV, or the CA is going to verify it and then register it. All right, the intermediate CAs are subordinate entities designed to handle specific CA tasks. So they process the certificate request and verify the identity of the individual. Now, we see a couple ways on here that a person can be authenticated. Emails, documents, we've done in person. Common method to ensure security and integrity of a root CA is it's kept in an offline state, away from the network. It's only brought online to handle specific and infrequent tasks. All right, a CR certificate repository is a publicly accessible centralized directory of digital certificates. It can be managed locally by setting up a storage area. Certificate revocation lists digital certificates have been revoked. The reason you may have a certificate that's been revoked is it's no longer in use. Details may have changed, like your address, or the private key has been lost or exposed. And a CRL is a list of certificate serial numbers that have been revoked. As an example of a CRL list. All right, the online certificate status protocol. This allows you to perform real-time lookup of certificate statuses. It's called a request response protocol. What this is, the browser is going to send out the certificates information to a trusted entity, and then that's going to respond back to let know whether there is a revocation information on it. And then there also is one of the OCSP stapling, sends it at regular intervals, timestamp response. All right, your three most common categories for digital certificates are your root certificates, your domain certificates, or your hardware and software certificates. Root certificates. These when you look at this, the process of verifying these are going to depend on your certificate chaining. Links several certificates together to establish trust between all the certificates involved. And the endpoint of the chain is the user digital certificate itself. So where it starts is going to be at the root. This is the one that's created and verified by a CA. And it's self-signed and does not depend on higher level authority. Now, between the root and the user, there can be more signature or certificates there that have been signed. And I did not mean to click that one. All right, so we look at this, we see that Equifax, for example, is the root digital certificate. Then it has some intermediates in between here, and then finally the user digital certificate. So these are things that they've been going through to build through this. Now, when this buyonline.com wanted to get a certificate, they had to go to one of these intermediates, and they processed all the information, and then finally it got up to Equifax. All right, so this is the certificate chaining for Cengage.com. And it's going to tell you here that the certificate is okay. This will show you some of the details for the certificate. All right, domain digital certificates. These are web server digital certificates. These are going to be issued to a web server or from a web server to a client. They have two primary functions. They ensure the authenticity of the web server to the client, and they ensure the authenticity of the cryptographic connection to the web server. And we got several different types of domain digital certificates. You got domain validation, extended validation, wildcard digital certificates, and subject alternate names digital certificates. All right, so what this is looking at this, it says, okay, the web browser sending out a client hello. So it's saying, hey, I'm here, I want information. Well, the web server receives that hello and it sends out an acknowledgement. It says, okay, we support your algorithm, we know who you are. So in there, it's going to verify the certificate and creates the pre-master secret. Then it's going to send the client key exchange, and then finally going to connect through. Excuse me. All right, the domain validation digital certificate verifies that the entity has control over the domain names. We see that it is listed as secure. The extended validation is going to require more extensive verification of the legitimacy of the business. Wildcard is used to not only validate the main domain, but also with all the subdomains. The subject alternate name digital certificate, it's also known as the Unified Communication Certificate. It's primarily used for Microsoft Exchange servers. Hardware digital certificates, you got machine digital, code signaling, code signing, and email digital. All right, your most widely accepted digital certificates are defined by a division of the ITU. It's known as the Telecommunications Standardization Sector. They adhere to the X.509 standards. They specify one of the three encoding formats listed here. All right, PKI, that's a public key infrastructure. This is a management tool for the use of digital certificates and also asymmetric cryptography. So things we're going to look at is how it's managed, how key management is performed, and no PKI trust models. All right, so PKI is the framework for all entities involved in digital certificates. Some of the actions they can perform is here is it can create, store, distribute, or revoke the certificate. Got a couple different trust models here. Trust is confidence or reliance on another person or entity. Trust model, it refers to the type of trust relationships that can exist between individuals and entities. Now, a direct trust is where one person knows the other. Okay, so you got a best friend, you're going to trust that best friend, hopefully. Third-party trust is where two people trust each other, or two individuals, two entities trust each other based off of mutual trust of a third person or a third party. The hierarchical trust model, and this assigns a single hierarchy with one master CA called the root. And then that can be used in organizations where one CA is responsible for only the organization's digital certificates. And then this, you have one person, one CI or CA who must verify and sign all documents. If you have that, you can run into limitation. They can fall behind, get overwhelmed. If that one private key gets exposed, everything in that organization is then, worthless. So this is an example here. We have our certificate authority. We have the hierarchical trust model. So everybody's using this. A distributed trust model is what we can use to eliminate the limitations of the hierarchical, as you're going to have more than one person or more than one entity signing digital certificates. So we have these intermediates that are signing these. This guy's over here signing these two, and they all go to the CA. All right, the bridge trust model is one CA acts as a facilitator to interconnect to all other CAs. The facilitator CA does not issue digital certificates, but it acts as a hub between the hierarchical and the distributed trust model and allows these to be linked. So we see here that we have our CA signing these, and we have our distributed here, and they have a bridge basically saying this one would trust this one through this person, or through this CA. All right, a certificate policy is a published set of rules that govern the operations of a PKI. And it's going to recommend the baseline security, the requirements to use the operations of a CA, RA, and other PKI components. The certified practice statements, it's a technical document that describes in detail how a CA uses and manage how the CA uses and manages certificates. So this also is going to cover excuse me, how to register for a digital certificate, how to issue them, how to revoke them, procedural controls, and key pair management. All right, we also have a certificate life cycle. All right, so we'll start out with the creation of the certificate. This is when you first apply for it. Your identity is verified. Then we go into suspension. This is something that may occur if the employee or the user is on leave of absence. It's not being used at the current time. Revocation is when it's no longer valid. And then you can also set an expiration on it, where the keys can no longer be used once the expiration. Some other things to look for key management is key storage, key usage, and the key handling procedure. Some means of public key storage includes embedding within a digital certificate, while means of private key storage would be stored on the user's local system. You can have software storage, but that can expose this to attackers. You can also store keys in hardware, smart keys, smart cards, tokens, things of that nature. Now, you can use dual keys if you need more security than what a single key provides. So a single set of public-private keys. One pair is used to encrypt information. The second pair is going to be used for digital signatures. You can also put your keys in escrow. Use key escrow, where keys are managed by a third party, such as your trusted CA. Private key is split in this situation in half. Each half is encrypted. They're going to be sent to the third party in two halves. And then the user can retrieve and combine those two halves to get the private key. Keys are set to expire after a set period of time, but you can also easily renew these. Keys can be revoked before they expire. Now, once they are revoked, you cannot go back and reinstate those. We have some other key handling procedures here for recovery. So you may need to recover keys for an employee hospitalized for an extended period of time. So this would use a key recovery agent. You may suspend somebody's key for a period of time and then reinstate it. Or you may just have the need to destroy the keys. So you remove all public and private keys and the user's identification. All right, so this is an example of the M of N control, where you have groups of people that you can control their keys. We have some cryptographic transport protocols, secure socket layers, transport layer security, secure shell, HTTPS, SMIME, secure real-time transport, IP security. All right, secure locking, or secure sockets layer. It's one of the most common. It was developed by Netscape. And the design of this was to secure the information between the client and a server. And SSL version 3.0 is the current version. And some of the things you can see here, you click on the little padlock. You can see the certificates that are listed there. You can see who it was issued to, who it was issued by, and the dates that it's valid from. It also shows you here what the purpose of the certificate is. You can look in here and see details. of it. So we see that we're on version 3. Serial number, algorithm, the issuer. See the path, who's signing this, and we can also view the certificate. And the issuer statement will open up here. Transport layer security. The SSL version 3 serves as the basis for it. They are more secure than SSL. You have a cipher suite. It's a named combination of encryption, authentication, and message authentication code. In here, you see the length of keys. It's a factor to determine the overall security of a transmission. Keys less than 2,048 bits are considered weak. 2,048 bits are considered good. And keys of 4,096 are considered strong. The secure shell, it's an encrypted alternative to the Telnet protocol. It's used to access remote computers. It is Linux and Unix based. It's got a suite. It's a suite of 3 utilities: the slogin, SSH, and SC. Now with this, the client and the server, the ends of those connections are authenticated using a digital certificate and passwords that are encrypted. And it can be used as a tool for secure network backups. HTTPS, it's a hypertext transfer protocol. It uses common use of the TLS and SSL. Secure version is actually plain HTTP sent over SSL or TLS. This is called Hypertext Transport Protocol Secure and uses port 443 instead of HTTP's port 80. And the URLs must be HTTPS. All right, so for example, if I pull up google.com, I can see this. It's going to tell me that it is a secure site. Okay, if you do not see the little padlock icon, you are not going over a site that's using HTTPS. And I don't think I have any that's test out. All right, test out, for example, here. See, it says not secure. Okay, so they're not using HTTPS to get to testout.com. And whatever I was linking to in that test out. But when I go just to test out, it is secure. Okay, so they have some things that are on their website that's not secure. That may have been an old link that I just pulled up as well. All right, the secure multi-purpose internet mail extensions. This is the protocol for sending secure emails, and it allows you to send encrypted emails that are also digitally signed. The secure real-time transport protocol. It is a secure extension. Protects the transmission using the real-time transport protocol. This is going to provide protection for voice over IP connections. IPsec is considered a transport security protocol. It's transparent to applications, users, and softwares. In here, it's got 3 areas of protection. It's going to correspond to 3 IPsec protocols. It's going to have the authentication, confidentiality, key management, and it's got 2 encryption modes. It's got transport, which encrypts only the data portion of the packets and leaves the header unencrypted, or tunnel, where it's going to encrypt both the header and the data portion of the packets. All right, so let's go to finish it up for chapter 4.